Hello all. The topic today is rocket motion. We all know what is rocket. We all play with the rockets in Diwali. The rockets that we play with in Diwali and the rocket that took human beings on the moon, they function on the same basic principle. The rocket consists of a long tubular body which is tapering at the top, and at the bottom it carries fuel. When the fuel is ignited, hot gases are formed inside the tank. Those hot gases produce a very high pressure, and the high pressure hot gases escape rapidly through a small hole present at the bottom of the rocket. As the hot gases escape in a downward direction, according to the momentum conservation principle, the rocket body acquires equal and opposite upward momentum. And that is the basic principle in the lift off of rockets. Rocket is a variable mass system. That is, as the hot gases escape from the bottom hole, the mass of the rocket decreases with the time. So the rocket becomes lighter and lighter during the liftoff. In variable mass system, because the mass change with time, to treat the variable mass system according to the laws of motion, Newton's laws of motion, first we have to determine our system. Determining our system means determining what mass is present in our system. In case of rockets, hot gases are being escaped. They leave the rocket. So in order to apply laws of motion to the rocket, we have to first fix our system. Means how much mass is present in our system. So at an instant t, suppose the rocket has mass m. Now the mass of rocket m is actually the mass of the fuel and the rest of the body. At the moment t, suppose the velocity of the rocket is v and the rocket momentum is mv. After the time dt, at a later moment t plus dt, the mass dm dash of hot gases leaves the rocket. The mass dm dash of hot gases leaves the rocket over the time interval dt, and therefore at a later time t plus dt, our rocket is little bit lighter and has a mass m minus dm dash, because the mass dm dash of hot gases has left the rocket system. The mass dm dash is called exhaust mass. So the change in mass of the rocket, dm dash represents the mass that have been ejected from the rocket. So the mass of the rocket changes by an amount dm, which is just the negative of the mass of hot gases which leave the system. That is, if dm is positive, means if the mass of hot gas that has left the rocket, if it is positive, it means that the mass of the rocket has decreased. So the mass of the rocket will be negative of mass of the hot gases. The rocket mass at an instant t plus dt will now be m plus dm. We replace dm dash or minus dm dash by dm, and we get m plus dm as the mass of the rocket at an instant t plus dt. The rocket velocity at the time t plus dt is v plus dv. Means dv velocity is acquired by the rocket over the time interval dt, during which the mass dm dash of hot gases escape the rocket. So the rocket momentum at the time t plus dt is its mass m plus dm multiplied by the velocity v plus dv. So we multiply out the two bracket and get this expression. So the change in rocket momentum in time dt will be, we saw that at time t the rocket momentum was p equal to m into v, and at a later time t plus dt, the rocket momentum is given by this expression. So the change in momentum over the time dt is subtracting mv from this. So mv get cancelled and we have the change in momentum of the rocket given by this expression. Then our system consists of ejected mass dm dash also. Now over the time dt, the mass of the rocket change by dm, means this amount of mass has left our rocket. But at moment t, our system consisted of the mass m, which is the sum of, which also includes the mass dm. At the beginning, the mass m includes the mass dm, which represent the mass of hot gases which would leave the rocket system in time dt. So our system actually consists of the entire rocket, and in time dt the mass dm of hot gases will leave the rocket, but it is still the part of our system. We are using the law of conservation of momentum in solving the problem of rocket propulsion. We do not have to care about what forces the hot gases exert on a rocket body to propel it in the upward direction. We simply have to apply the law of conservation of momentum and we get much about the rocket propulsion problem solved. So, the law of conservation of momentum means before before uh, before the hot gases escape, the total momentum of the rocket, and after some of the hot gas escape, the total momentum of our system, the two momenta must be same if there is no external force. So the momentum at time t was simply the mass into velocity of the rocket, and the momentum at t later time t plus delta t is this momentum. This is the momentum only of the rocket. This is the momentum only of the rocket. But we also have to see the momentum of the mass of hot gases which have escaped over the time interval dt. So for our system, the momentum, total momentum of our system at the time t plus dt is the sum of the momentum of the rocket body plus the momentum of the hot gases leaving the rocket. So we now turn towards finding the momentum gained by the mass dm dash. The mass dm dash gains the momentum mass multiplied by its velocity. Now v plus dv is already the velocity acquired by the rocket when the mass dm dash has escaped from the rocket. So this is the velocity of rocket body, and the velocity vex, represent the velocity of this escaping mass dm dash, but relative to the rocket body. This velocity is the velocity of escaping gas relative to the rocket body. So velocity v exhaust, it is the exhaust velocity. It is called exhaust velocity. Exhaust velocity is not measured relative to our coordinate system, but it is measured relative to the coordinate system attached to rocket body. So what is the velocity relative to our coordinate system? Velocity relative to our coordinate system, let's call it VO, of the escaping gas is equal to velocity of rocket plus the velocity of exhaust mass relative to the rocket. Velocity of rocket plus velocity relative to the rocket is the velocity relative to our own coordinate system. And therefore the momentum acquired by the mass dm dash relative to our coordinate system will be the mass dm dash multiplied by its velocity relative to our coordinate system. So this is dm dash velocity of rocket plus the velocity relative to the rocket, and velocity of rocket is v plus dv. So we replace velocity of rocket by v plus dv here and the exhaust velocity here. Now we have a negative sign because the exhaust velocity is in downward direction. and this exhaust velocity is measured with respect to rocket. So with respect to rocket, the exhaust velocity is positive, but with respect to our coordinate system, the exhaust velocity should be negative, and therefore with respect to our coordinate system, we have a negative sign attached to the exhaust velocity. So this is the momentum gained by exhaust mass, and this is the change in momentum or the momentum gained by our rocket. So total change in momentum is the sum of these two momenta. Momentum gained by the rocket plus momentum gained by the exhaust mass dm dash. So here we have total change in momentum. The change in momentum of rocket body plus the change in momentum of the exhaust gas. Now we know that dm dash is just the negative of dm. Dm dash represent the mass that has escaped the rocket, and dm is the change in mass of the rocket. So they are negative of each other. The mass that is escaping and the mass by which the mass of the rocket changes, they are negative of each other. So we replace dm dash by dm. We replace dm dash by dm. Now why are we doing so? Because in our derivation of rocket propulsion, we are going to describe the rocket motion, and therefore we try to keep the mass of rocket everywhere in our expression, everywhere in our analysis. We do not want to keep the mass of the exhausted gas, because we are interested in the motion of rocket and we must include the mass of rocket everywhere in our analysis. So this is the reason why we change it. So here we will see that dmv is negative, minus dmv and plus dmv will get cancelled, and we get this dmdv and dmdv also get cancelled, and we get the change in momentum. It is very simple to see. Now we know that the rate of change of momentum of the system is equal to the net external force acting upon the system. This result, we know this result from the system of particle. In our system, the Newton's third law of motion is obeyed. The exhaust mass which escape in the downward direction exert equal and opposite force in the upward direction on the rocket body. So Newton's law of motion is obeyed between the two parts of our system. One is the rocket and other is the exhaust mass. It is dm dash, not dm. It is dm dash. And whenever the third law of motion is obeyed in a system, we can write the equation of motion for that system as the net rate of change of momentum equal to the net external force. The internal force will not be present in this expression, because internal forces being equal and opposite will cancel out each other and will not present anywhere in our analysis. That is the basic result for the system of particle where the third law of motion is obeyed. So the change in momentum, as we have already found, is mdv into vex dm. Here we got the change in momentum. We substitute for the change in momentum, and this change in momentum occurred over the time interval dt. We have substituted that change in momentum here and we get this equation. So we split the equation dv, we take dv by dt and dm by dt, and finally get an equation, the basic equation that describe rocket propulsion. The external force is basically the force of gravity which act in a downward direction. We rewrite this equation in this form. So what we see on the left hand side is the mass of the rocket multiplied by its acceleration. So that represents the net force acting upon the rocket. And the net force acting upon rocket consists of the two forces on the right hand side. One is the external force of gravity, and other force is represented by this term. The force of gravity act in a downward direction. So the only force responsible for propelling the rocket in the upward direction is represented by this term, and this term is therefore called thrust on rocket. So this is the thrust, upward thrust or up thrust acting on a rocket. We now consider the case when the external force is zero, which happens when the rocket is cruising in free space where there is no force of gravity. When external force is zero, we remove the external force term from the equation and we get this equation. We set external force equal to 0 and rewrite the equation for the case of net external force equal to 0. So dt cancel out and we get this equation. Now we adjust the equation and separate the variables. We take variable of mass on one side and the variable of velocity on the other side. So this is what we have done here. We have see, mass will not be present on this side, it's a mistake. So dv equal to exhaust velocity m into dm. Now during the liftoff, the velocity of the rocket changes from say v0 to v, and at the same time its mass changes from m0 to m. The way these changes have occur can be understood by integrating this equation. So we integrate this equation, we integrate left hand side from the velocity v0 to the final velocity v, and the right hand side is integrated from the initial mass of m0 to the final mass m. Now, if the exhaust velocity is constant, which is often the case, that the exhaust velocity, the velocity with which the hot gases are escaping the rocket, is almost constant for most of the cases. So, we assume this velocity to be constant and take it outside the integration, and the rest of the integration, as can be readily seen, is easy to perform. So, for the case of external force 0, we finally obtain after the integration on the left hand side v minus v0, and this is what we get on the right hand side. So, looking at this expression, we find that as the time passes, the mass m of the rocket decreases and the value of this logarithm increases as the time passes, and therefore the velocity gained by the rocket, which is v, also increases with the time. Here we see that the increase in the velocity of the rocket depends upon the exhaust velocity and the ratio of initial mass of the rocket to the final mass of the rocket. So how fast the gases are being burned, how fast the fuel is being used, it does not determine the increase in the velocity of the rocket. The increase in the velocity, whether you burn the fuel slowly or whether you burn the fuel faster. Okay, intuitively we might feel that if you burn the fuel faster, the rocket will acquire higher velocity, but it doesn't happen so. Whichever the rate at which the fuel is being used, the final velocity depends only upon the ratio of initial and final mass and the exhaust velocity of hot gases. So if initial velocity is 0, we rewrite this equation. The final velocity, which is v, if we start from 0 velocity, that is from the launch pad, the velocity v is given by this equation. Now, if all m represent the final mass of the rocket, and when all the fuel is exhausted, we have a certain final mass of the rocket. When all the fuel is exhausted means the mass of the rocket is no longer changing, mass of our system is no longer changing. When all the fuel is exhausted, we have a certain final value for the final mass of our system, and that final value of the mass determines the final velocity, the final highest velocity that our rocket can attain. So final velocity attained by the rocket depends upon what is the final mass of our system when all the fuel have been used and exhausted, and the initial mass of the rocket. The mass of the fuel is usually very large as compared to the rest of the rocket body. So for example, if initial mass of our system is 90% fuel, then the ratio of the initial mass of our system to the final mass will be 10. It's easy to see. The initial mass m0 may be written as uh, So initial mass is 90% of the fuel, and when all the fuel have been used up, 90% of the mass is lost, and our final mass of our system will be only 10% of its initial mass, and 10% of its initial mass means it will be simply m0 divided by 10. So our final mass is simply m0 divided by 10, and therefore m0 upon m will be equal to 10. The ratio m0 upon n will be equal to 10. We substitute for the ratio equal to 10 in this example, in this equation, and obtain the highest final velocity our rocket can attain for a given exhaust velocity for the case of 90% fuel used in our rocket. Thus, the highest final velocity is Vx multiplied by log 10, and it is only 2.3 times the exhaust velocity. So, we see that the final velocity of rocket is not too high as compared to the exhaust velocity when 90% of the mass of entire rocket system is a fuel. So what we will have to do to have a highest final velocity of the rocket? We will have to increase the exhaust velocity. So rocket engineers try to somehow increase the exhaust velocity of burnt fuel, and then we can increase the highest velocity our rocket can attain. The highest final velocity of the rocket VF can also be increased by using multi-stage rockets. Instead of using a single tank for the fuel, we use multiple tanks for the fuel. Some of the tanks are burnt in the first stage of propulsion, and those tanks which are burned in the first stage of propulsion, they are automatically removed so that the mass of the rocket can be reduced for the next stage of the rocket. For example, initial mass of the rocket is m0, and when the first stage of the rocket is done, the fuel tanks are automatically removed, they are jettisoned. So the final mass of the rocket when the first stage is over is actually m. But when we remove the fuel tanks, the final mass of the rocket reduces still further, say by m dash. And now this reduced mass will be the initial mass for the second stage. So for the second stage, the initial mass is smaller, and that initial mass for the second stage then further decrease at the end of the second stage to some final mass. Final mass is say m3. Say this is m1, this is m2. So final mass is m3, and final mass m3 will also be small as compared to the case when the tanks are not removed. When we use a single tank of fuel, we cannot remove it in the middle of rocket propulsion, and we will have to carry that entire tank during the entire rocket propulsion process. But if the multiple tanks are removed, then once the fuel is exhausted in those tanks, the tanks can be removed and the mass of the rocket can be reduced. So this reduction in the mass of the rocket causes the reduction in the initial mass and the final mass of the rocket at the later stage. And the reduction in the initial and final mass in the later stage of the rocket increases the ratio of initial mass to the final mass, which in turn increases the final velocity attained by the rocket, because the velocity attained by the rocket also depends upon the ratio m0 upon m. So if we have methods of increasing the ratio m0 upon m, we can further increase the final velocity attained by the rocket. Thank you for watching the video.